Hi everyone, thanks for checking out this video. So in this lesson, we're going to be talking about the predator-prey model, which is a very common model used in ecology to model populations where one species is a predator and another species is its prey. So this model was developed by Alfred Lotka, an American mathematician, and Vito Volterra, an Italian mathematician, in 1910. And it's very popular in ecology, and it also has some applications at the microbiome level, which I think are especially interesting. So I'm going to put a link in the description to a really interesting paper that talks about applying this model to bacteria, like predator-prey interactions in bacteria populations. But that's sort of uncommon, and most of the applications are about predator-prey interactions at the animal population level. So, for example, like foxes and rabbits, or like sharks and smaller fish. And so I think in this example, we just for the purpose of this example, we'll be talking about bears as being the predator and fish as being the prey. So X will be fish and Y will be bears. So maybe just to help us keep track, I'll just draw these really quick. Fish and then okay. Yeah, so this lesson is actually a two-for-one deal because in addition to telling you guys about the predator-prey model, I'm also giving you guys a free art lesson. So this is your art lesson on how to draw a bear. So this is a bear here. Okay, so let's get started. So this term here is going to be our growth term for the fish population. So we have a constant alpha multiplied by x, which is the current fish population level. And the reason for this is that the growth rate of the population depends on the current population level. Because if you think about it, populations, unless they hit some carrying capacity or something stopping them, they'll grow exponentially as they like keep multiplying. So that's why we have some constant growth term times the current fish population level. And then we have our death term here. So we have a constant beta times the current fish population level, and then also times the current predator population level, the current level of the bear population. Because the death rate for the fish depends partly on bears eating them, so that's why we have y in this death term here. Okay, and then so for the bear differential equation, so this is the growth term here. We have a constant delta, um, and we have same as with the fish. It's multiplied by y, which is the current bear population level, because that's how populations grow. There needs to be some bears for more bears to be produced. And then this is also multiplied by x, the fish population level, because the growth rate for the predator actually depends on their being able to get something to eat. You know what I mean? So there has to be, if the bears can't get anything to eat, if they can't eat the fish, then their population isn't going to be growing as much. So for the bear population to grow, there needs to be enough fish that they can get enough to eat. And then we have our bear death term here, which is the constant term gamma times the times y, which is the current bear population. So pretty straightforward. So next, let's talk about some steady states. So if you guys remember, the way we find a steady state is just by setting the derivatives equal to 0, because we're looking for a steady state means no change happening in the population levels, and the derivative is the rate of change. So if we set the derivatives equal to 0, that just means there won't be any change happening. So the first one we can talk about is kind of the trivial one of both of the populations being at 0. So I'm putting this here to be kind of like mathematically precise, but this is really like not that interesting. If we don't have either of x or y, that's like technically a steady state. But there's also a non-trivial steady state to this system that we can solve for. So we'll solve for that by setting the derivatives equal to 0, and then we can sort of pull it on this side, pull an x out, and then we get so x times alpha minus beta y. So that's for what we'll be solving for this equation. And then for this equation, we can pull a y. We can pull a y out of this side, so we get actually, yeah, pull a y out, and we get delta x minus gamma. And then we can think about how do we make these sides 0 other than just the trivial example of setting x and y equal to 0. So the other solution is we can make y alpha over beta, and we can make x gamma. Sorry, it's gamma over delta. So this is the other non-trivial steady state. So it's gamma over delta for x, and then alpha over beta for y. Sorry about the bad handwriting, but yeah. So this is the other. So we have our steady state of just zero of both, and then our non-trivial steady state of gamma over delta, and then alpha over beta. So before we actually do the simulation and like plot the results, I think for these kinds of systems, it's a good like mental exercise to see if you can figure out what the dynamics will be like intuitively rather than just plotting and graphing results. If we can like if you guys want to just like think intuitively what will happen here and see if you can figure it out. So like what will happen to the bears if they run out of fish, and then what will happen to the fish population if the bear population decreases. So in the next lesson, we're going to actually like do the Python simulation and like actually plot the results so you guys will see. But just for like a mental exercise, I think it's good to just like think about it and maybe see if you can use like intuition to figure out what's going to be the dynamics here. Okay, but yeah. So next lesson, we're going to actually do the simulation in Python, and you'll see. So thanks for watching, and see you next time.